All right, let's dive into one of the most profound, most important unanswered questions in all of computer science. Seriously, this is a puzzle so fundamental that there's a $1 million prize waiting for whoever solves it. We're talking about P versus NP.
Now, at its heart, this incredibly complex topic comes down to a really simple, almost beautiful question. If you can easily check that a solution to a problem is correct, does that mean it must also be easy to find that solution in the first place? That's it. That's the fundamental mystery we're going to unpack today.
So to get to the bottom of this, we first have to understand how computer scientists actually classify problems. Let's start with the most straightforward category, which is known as class P. P stands for polynomial time. Now, don't let the name scare you off. It's just a fancy way of saying a problem is easy or efficiently solvable for a computer. What that really means is, as the problem gets bigger, the time it takes to solve it grows in a predictable, manageable way. It doesn't just explode into needing centuries of computation time. You deal with P problems all the time. Think about sorting a list of names alphabetically, or finding the shortest route on a map using an app, or even just searching for a contact in your phone. These are all problems in class P. Even if you have a massive list or a huge map, a computer can still handle it pretty quickly, because the complexity is manageable.
Okay, so that's P. Now we're going to step into a much bigger and way more mysterious category of problems. This is class NP.
NP stands for non-deterministic polynomial time. And here's a super common mistake. A lot of people think the N means non-polynomial. It absolutely does not. The key here is that if someone just gives you a potential solution, you can verify whether it's correct really efficiently in that same polynomial time we just talked about. So the focus shifts from finding the solution to just checking it.
You know, the perfect way to think about this is a big Sudoku puzzle. If you're staring at a blank, complex grid, trying to solve it from scratch, well, that can be incredibly hard, right? It could take you hours of trial and error. That's the finding part.
But what if I just handed you a completely filled out Sudoku grid? Checking my work to see if it's a valid solution is a piece of cake. You just quickly scan every row, every column, and every little box to make sure there are no repeated numbers. It's fast, it's simple. That's the verifying part. And that is the soul of an NP problem.
So this leads us to a really crucial relationship. Think about it. If you can solve a problem efficiently, meaning it's in class P, then you can obviously verify a solution just as fast. You could just solve it yourself and see if the answers match. This simple bit of logic means that every single problem in class P is also, by definition, in class NP.
But inside this huge world of NP problems, there are some real monsters. This is where we run into what you might call the boss-level problems, the absolute hardest of the hard.
First up, we have NP hard problems. A problem gets this label if it's at least as tough as the hardest problems you can find in NP. So here's a way to think about it. If you had some magical computer that could solve an NP hard problem, you could use that same machine to solve any problem in NP. That's just how fundamentally difficult they are.
Then we have NP complete. A problem is called NP complete if it checks two boxes. First, it has to be an NP so we can check answers quickly, and second, it also has to be NP hard. These problems are kind of the crown jewels of complexity theory. They are the absolute hardest problems that we know of inside the class NP.
And the most famous example of this is the traveling salesman problem. Imagine a salesman has to visit, say, 50 different cities. Finding the absolute shortest route that hits every city just once is a monstrously difficult problem. The number of possible routes is just astronomical. But if I give you a specific route and I ask, hey, is this route less than 10,000 miles? Well, you can just add up the distances and give me a yes or no answer super fast. Finding is hard. Checking is easy. Classic NP complete.
And the traveling salesman is definitely not alone. This special class of problems pops up everywhere, in fields from logic like Boolean satisfiability all the way to network design. And even though they all look different on the surface, they're all computationally tied together. If you could solve one of them efficiently, you could solve them all.
So, this all brings us back to why any of this theoretical stuff actually matters. Why is it a $1 million question? Well, because the answer has some incredibly profound real-world consequences.
And here's the bombshell. Because all those NP-complete problems can be sort of translated into one another, they're all deeply linked. If some brilliant researcher discovers a fast, efficient polynomial time algorithm for solving just one of them, doesn't matter which one, it would be like finding a master key that unlocks every single one of them. A fast solution for one would mean a fast solution for all of them, which would finally prove that P actually equals NP. And that, well, that would change everything. On the one hand, modern cryptography, the stuff that protects our banking and all our data online, it's all built on the assumption that certain problems are just too hard to solve. If P equals NP, most of that encryption would be instantly breakable. But on the other hand, it would also kickstart unbelievable advances in medicine, logistics, artificial intelligence, you name it.
And just to make things a little more interesting, there's a new player on the field, quantum computing. These machines don't think in ones and zeros like our computers do. They work based on the bizarre principles of quantum mechanics, and it's believed they might be able to solve certain NP problems, like the one that underpins most encryption, way more efficiently than any normal computer ever could. Now, this doesn't necessarily prove P equals NP, but it could completely rewrite our understanding of what's computationally possible.
Okay, let's just take a quick step back and visualize how all of these classes actually fit together. It'll help to see the whole picture. So here's how it all lays out. Imagine a big circle that represents all the problems in NP. Inside that, you've got a smaller circle for P. Those are the problems we know we can solve quickly. The whole million-dollar question is whether that little P circle is actually the exact same size as the whole NP circle. Now, also inside NP are the NP complete problems, right at the core, the hardest of the hard. And finally, you see the NP hard circle? It totally contains all of NP complete, but it also stretches outside of NP. That's because a problem can be at least as hard as NP without its solutions necessarily being easy to verify.
This table gives us a nice, clean summary. So, class P, solvable fast, like sorting a list. Class NP, verifiable fast, like checking a Sudoku. NP complete, the hardest problems that are still inside NP, like our traveling salesman. And finally, NP hard, problems that are at least as hard as anything in NP. A classic example there is the halting problem, which is so hard it isn't even verifiable in NP. That's proof that the NP hard class really does extend beyond NP.
And that brings us right back where we started. Is that creative spark of finding a solution really the same fundamentally as the mechanical process of just checking it? Is P equal to NP? Despite decades of work by the smartest people on the planet, nobody knows the answer. It could unlock a whole new era for humanity, or it could just confirm that some problems are and always will be fundamentally hard. For now, it remains one of the greatest unsolved mysteries in all of science.